Thank you, Tim. Pleasure to be here. Thanks ever so much for such a wonderful opportunity to speak to you all. Just to set some context, as Tim indicated, this is a little bit of a change in gear. There's going to be a little bit of technical stuff, but we're a tech developer. We've been developing technology for recovering value from waste streams. And so our export, if you like, is technology. So we develop technologies in New Zealand and we export them overseas. I think this is not going to be a secret to anybody. Digging metals out of the ground is unsustainable. We've been digging metals out of the ground for many hundreds, if not thousands of years, but it is coming to a stage where it's becoming completely unsustainable. The challenges we're facing is obviously the demand is increasing year on year, particularly for some niche metals that are used in decarbonisation, electrification technologies. The natural resources are depleting. We've dug through an awful lot of all the high grades of materials. Gold, for example, 100 years ago we were digging a kilogram of gold out of a ton of rock. Today we're digging about 2 grams of gold out of a ton of rock. And the environmental impact of doing that is just horrific. And not just that, but obviously taking the embedded metals out of the rocks and turning them into pure metals, it has an incredibly high carbon footprint. And metal refining is responsible for about 7% of our greenhouse gases. So, as I say, we develop technologies that do deliver those circular metals. And why does anybody care? Well, a lot of these metals are absolutely critical to to future decarbonisation technologies. So, in fact, they're called critical metals because they are literally critical for those future technologies. Technologies like IT, technologies, data centres, wind turbines require rare earth elements. The EV revolution that is slowly coming along requires lithium, cobalt, and nickel. So there's governments all around the world who are focusing on these key niche metals that are literally driving into the future. There's many different mandates, different policies in different countries, and we are there to kind of develop our technologies and take them into new countries. In addition to that, there's of course the kind of corporates of the world who are also driving change. A lot of these big corporates have net zero targets, aggressive net zero targets, so really looking to green up their or decarbonise their supply chains. A lot of electronics manufacturers, for example, a lot of EV manufacturers have a real strong need for metals that are going to feed the future supply chains. It's largely driven by you and I, and our desire for having cleaner, greener products in the future. So it is a little slow in coming, but there is real change happening, so real demand there. So, as I say, we've developed technologies for recovering value from waste. Now, waste streams are typically, again, we're also responsible, you and I are also responsible for waste streams. They're typically created in urban environments. They're typically created in the cities where you and I live. And so if you're looking to capture the value of those different waste streams, particularly the metallic value of those waste streams, you need to have technologies that can be placed in city-scale environments. And that's exactly what we've developed. We've developed a technology for recovering recovering metals from waste streams and doing it in cities where those waste streams are produced. So we've developed technology that basically slides into existing warehouse infrastructure. It's a clean, green, low-carbon process, so it recovers metals in real time from waste streams as they're produced. And then because you're recovering those metals in those city environments, you're able to return those clean metals, those low-carbon metals, directly back into the city or the local infrastructure and kind of really close that circular loop. It's low carbon, which is important. Obviously, digging metals out of the ground has that massive carbon footprint. Recycling these metals in a low carbon way is what we do, and then our ability to deploy these plants locally is driven by the low-cost nature of the technology. So we deploy these really low-cost plants that are able to take very, very significant amounts of metals that are produced locally and recycle them locally. So that's the high-level bit. This is the more techie side of things. This is actually what we do. So a couple of waste streams that we deal with. First one, electronic waste. So we take things like old cell phones, old laptops, server blades, and everybody knows they contain metals. The challenge is that they actually contain very, very tiny, tiny traces of gold, but that gold is by far and away the most valuable part of that waste stream. And so you've got to grab the gold, if you like, in order to pay for your process. Because there's a bunch of other metals floating around, you've got this real problem of a needle in a haystack. So what we do is we dissolve all of those metals into solution. We use a biomaterial that we've developed ourselves to go into that solution, selectively suck up the gold and only the gold. And because this has got mass, you basically use it as a sponge to pull gold out of your solution and refine that up into a pure metal. That enables us to recover the gold. Then we can use much more conventional chemistries to recover the other products, so the copper, the tin, the silver, and recover all those other metals. Been doing that for a while, and when we realise what we're good at, and good at pulling specific metals out of waste streams, we apply our technology to things like lithium-ion batteries and able to recover lithium, nickel, cobalt from other waste streams. Again, in that local, low-cost, take the plant to the waste stream way and recycle those directly back into the local economy. As I say, we've been doing this for a little while. It's been a pretty stereotypical venture-funded journey to date. You kind of start these things in test tubes and you scale up. We've built our first commercial operation in Sydney, and that's been operational this year, and essentially taking all of Sydney's e-waste and recovering serious amounts of copper and gold from those waste streams. If you're looking to build a plant like this in a city, it's got to be clean and green. You can't produce any nasties. It does slide into an existing warehouse. It doesn't produce any off gases. Doesn't produce any waste streams that can't be dealt with by clean water. Uses local power, local water, all those sorts of things. So it just ties in directly, and that enables us to kind of just very, very easily slide this into an existing warehouse, literally anywhere where these waste streams exist. So that's Australia, and that's kind of been the journey to date. Obviously, that has little to do with the US. So the next step for us is how we actually get into the US. When we kind of look up from where we're at, what we've created, this fantastic technology that is very, very exportable. We see all roads do lead to the US for technologies like this. There's extremely strong policy around critical metals. There's obviously a lot of venture capital in the US. But also, as waste producers, the US is a very, very large waste producer and a very, very high-tech society. So an awful lot of these, very, very attractive streams for us. So when we looked up, US is kind of all things lead to the US. Time to take our technologies to the US. We've literally a couple of days ago signed a lease for exactly the same warehouse in Texas, and about to build this next plant. There's an opportunity to build several of these plants across the US, and that's the journey we're on right now. Starting with a plant in Texas, a Longview, it's about 3 hours north of Houston, and then a view that we can build these plants, essentially the same plant. All around the world, everywhere where these waste streams exist. That's it. I think I've got 5 seconds left, so I've done fairly well. So I don't know if that means... When do we do questions? Is that now? Or? Do them after. Thank you ever so much for your attention.
Thanks very much, Will. That was impressive time management. It's now my pleasure to introduce Professor Delwyn Moller, who is going to take us skyward and talk us through some of her international research that demonstrates how aerospace innovation is helping to tackle global challenges from above. Delwyn is a leader in the development of novel remote sensing systems, primarily with application for earth sciences. She's a professor at Waipapa Taumataro, the University of Auckland, and has an incredibly impressive resume that includes NASA missions, multiple awards in innovation, and a knack for turning complex science into practical solutions. Over to you.
Thank you for the kind introduction. So, yes, what I'm going to be talking about today is just a couple of missions, one which is suborbital, and it's happening as we speak, probably flying right now, and a second which is more of a futuristic, hopefully not too futuristic, mission concept, and both of these are international collaborations. So I'd like to just kind of put a backdrop here in terms of what I used to call the changing face of space. I think it's now the changed face of space. And so I've got here just a snapshot of a few of these, what we might call new aerospace companies, or the face of where things are at the moment, and balance between a couple of US ones and a couple of New Zealand ones. And we have a lot of strength in New Zealand. And CEO of one of them is right here, Mark Rocket, I'm looking at him. And I'd like to bring home that, we have, within aerospace, it truly is aerospace, and I'll give you the reason as why I see it that way in just a moment. So, all of these advanced platforms and the increased access to them and accessibility is awesome. My background is mostly the major space agencies, but now there's a lot more accessibility. And so that creates new capabilities, really. And so these platforms are as good as what we do with them. What are we going to do with them? What are we going to put on them? Are we going to go to another planet? Well, in my case, I like to look at this planet. And each time that a new capability comes online, that provides new possibilities for science and observations. And there's no one-stop shop. The Earth is complex. So we want to think intelligently about what it is we're trying to measure, and then come up with the appropriate solution. And so here I've got, the range of different scales of observations and things you might marry with that. In this case, I've put in a radar because I do radar remote sensing. But I'm going to start by focusing on the middle one, which is terrestrial monitoring. And so what we have going is a really cool mission, and it truly is a mission. It's flying for 7 years, and we have a sensor, a NASA sensor, on an Air New Zealand aircraft. It's a Q300, so it flies domestically, and it's giving us kind of unprecedented observations of New Zealand. So, these kinds of observations we can do for, basically we're getting observations for food security, water security, implications around that on a New Zealand scale, okay? We make pictures, so that's the best way that I can kind of drive home what we're able to do here. And if we look on the left, here's a zoom in. You saw the coverage of what we're getting in New Zealand, but really to see the detail, this is a single month worth of data. And where we're seeing, you can see where we're seeing inundation, coastal observations, but you can also see that detail and that drying and wettening. Basically, the color scale is showing us where we're getting healthy vegetation, healthy soils, or wetness of soils and drying of soils. As we do this month by month, we can see changing patterns, and we can see that on paddock scale. This is complementary to what you can get from space. At space, we see it on a much larger scale, but here we can see it at relevant for land use scales. So what we're doing here is unique yet complementary. If we look at the right-hand side, we're looking at coastal inundation. This is one flight's worth of data. So what we can do is get that data within 15 minutes of landing. So very low data latency ability to get reconnaissance for things like flooding, etc. So moving on, that's all great. We're doing this in New Zealand, but what about, where's the relevancy beyond New Zealand? Well, what we have here, if we took this and basically took signals of opportunity, we're just listening to GPS signals, it's a very passive system, and put that on other payloads of platforms of opportunity, like commercial aircraft that are flying anyway. Here's an example of what kind of coverage we could get over Luxembourg. So we actually briefed Luxair, which is the equivalent of our Air New Zealand for Luxembourg, and said, if we put these on your fleet of 11 Q400s, this is the kind of density you could get and the kind of information you can get. This is just 6 weeks of flying. And if you look at that, it has huge implications for transnational agriculture, and so food security and also water security. And I've got to keep moving along. Okay, so let's take this into our next example, the case for space, okay? And I'm going to talk about maritime domain awareness, and reason for that, the ocean is big. Okay, and synoptic monitoring of our oceans is a very topical, as we heard this morning, subject. So we have put together a mission concept that I'm going to share with you in a moment. But if we look at the view graph here, basically this is around our shared Pacific priorities. And if you look, we have our neighbours in Australia. They've got a lot of the same needs, observational needs and issues that we do. And you have on the map there our EEZ, or EEZ, bilingual, and also our search and rescue zones. These are big, large areas, and right now they're very inadequately monitored. If we talk about maritime domain awareness, it's a really expansive term. It's basically everything to do with our oceans, health, monitoring, etc., management, economy, environmental, all of the above. The mission that we're working on at the moment kind of focuses on a few key aspects that is really a missing element in terms of observations that will enable us, hopefully, to be able to do a better job. But if we step back just for one moment, there's a lot of progress going on in the commercial sector, and so it's like, well, why would we want to have our own capability or design our own mission? Why not just buy data? Well, there's a couple of reasons, but one is basically economic. Our EEZ is so large, it's prohibitive. Even if we could get that data, it would be prohibitive, even just for New Zealand's EEZ, to procure commercial data for one time. So there's just a basic mechanism there that we want to address. But there's also technical aspects. So if we think about synthetic aperture radar, which is a very popular tool that's used for maritime domain awareness, there's a basic, you run into a basic trade space, basically, and there's a limitation. At some point, the ocean becomes very large and very noisy if there's high sea states, and the objects become very small and difficult to see. So there's a detection problem, and there's also a knowing where to look problem. So this has been going on since the 70s. So CSAT was launched in the 70s, and people have been working on this, a lot of smart people, for a long time. So it's an old problem. Whenever you have an old problem, you want to find a new way to approach that old problem, and that's what we're presenting here. In the meantime, if you look at the lower right graphic there, we're now getting a proliferation of USVs, unmanned surface vehicles, and right now these are currently basically undetectable using classic SAR radar. They're on the order of 4 to 8 meters. So I consider that this is kind of the new goal of what we want to be able to detect. So we have a mission concept that first actually has some NASA heritage from some work I did on a marine debris workshop there, but now got put together with a DLR collaboration and is now a collaboration with our Australian partners at SmartSat CRC. And this does have a new element to it, where we've got 2 formation flying spacecraft that are basically forming a multi-static SAR and using interferometry. And so that's our, it's future thinking, it's using capabilities that are here that we could employ, but it really is pushing the state of the art beyond what's currently available. And it's a fundamentally new approach, and I have 30 seconds, so I'm going to end on the next one, which was, okay, it is a new approach, no one's done this, and in our collaboration with the DLR, they have a spacecraft, or a pair of spacecraft called TandemX, and what we did was we came up with a proof of concept experiment. And when the spacecraft were in a configuration that we thought we could maybe get some usable data, we flew it over, they targeted Lake Hawea, and we're out on the lake with a Coast Guard vessel. And we put a little floating mat. If you see that in the far lower right corner, it's basically a pool mat, 2 pool mats together. We put it over the side. This is a pretty, we thought, if we can see this, we'll be amazed. Well, what do you know? So if you look at the middle graphic on the right, the one next to the boat, you can see the platform shows up quite nicely in the image. The ship shows up quite nicely in the image. To the right where the circle is where the platform is. You can't really distinguish it from the surrounds. But using this new technique, so the next graphic to the right, I wish I could point, is the interferometric detection. And again, you see the platform, you see the Coast Guard vessel quite well, and even that's a small target. Next to it, you can see the platform. This little set of rubber mats show up. This is not in any way optimized in the way that our Takahe mission would be, but the fact that we can see that gives us great encouragement and has hopefully led to continued partnership with our Australian partners because they're pretty excited too. And I'm out of time, so I'll leave it at that.
Thanks very much, Delwyn. You did very well to fit so much into 10 minutes. I've got a couple of questions here. There's a few that have come through from Slido as well. We've got 5 minutes, so we might do rapid fire questions, if that's all right. But Delwyn, I'll begin with you. The Rongawai project that you showed, I thought it was great that you were sort of, you explained how you're working in partnership with Air New Zealand, of course, one of the sponsors of today's summit, so it was good promotion. But what would it take to take that further and to get that into other commercial aircraft?
Well, actually, it's quite achievable, and the reason it is, and I'd like to say that in today's environment, I think it's actually harder to put something on a commercial passenger airline than it is to put something in space. The safety aspect of things are pretty amazing because there's people on board, but Air New Zealand has kind of, in doing the original development, in terms of the certification and everything we needed to go through, we managed to get through that barrier, and so I think the next time around is going to be so much easier because they've already done what really was the hard part of it.
Oh, fantastic. And Will, a question for you. You mentioned Texas being your first sort of site in the US. Can you tell us a little bit about what the decision making was like for choosing Texas? Why Texas, and how is it going?
Sure. Is this on? It is. Perfect. So yeah, as I say, when we look up, we look at the US being kind of the holy grail for electronic waste. And then we start looking at states, and that's the challenge with the US is you've got kind of 50 countries in one place, and so we've got a rapid screen of where the best places to build a business like ours are. It comes down to where the waste streams are concentrated. Texas floats to the surface for a number of reasons. There's a whole bunch of data centers there. There's a bunch of cities that have pretty high densities. It is a very business-friendly state. It's typically a red state. Well, not typically. It is a red state, but it also has actually some very high recycling rates compared to a lot of the other red states. So it floated to the surface for a number of reasons. And then the economic development agencies there were also very, very proactive. So it ends up a good place for us to start our journey.
Yeah, great. There's a question that's coming on Slido for you as well. Have a crack at answering this as quickly as you can, but it asks, what is the revenue model for Mint? Is it purely the value of the metals retrieved, or are you paid by councils?
It's purely based on the metals that we retrieve. A ton of material, a ton of waste material contains about $15,000 worth of gold and about $2,000-3,000 worth of copper. So they're actually really, really valuable waste streams. Be lovely to be also paid for it, but we've got to base our economics on essentially recovering value from scrap.
And Delwyn, the Project Takahe that you sort of touched on towards the end there, what are there opportunities to work with the US on that project?
I would greatly hope so. I was at a NASA workshop about a year ago on bistatic and multistatic SAR, and honestly, there's two world leaders in terms of, it's a fairly niche field for this kind of thing. The world becomes very small quickly in that expertise, and the leaders would be Germany and NASA, frankly. So yeah, I'd very much like to, yes.
Yeah, cool. We've got just over a minute left, and I wanted to ask a question about AI and big data, because I don't think you can have a tech panel where that is not mentioned these days. So I wondered how, if at all, either of you are using big data or AI.
We don't use it to a great degree, but interestingly, the AI and big data requires massive electronics infrastructure, data farms, server farms, data centers, and these things last 2 or 3 years. So they're actually becoming a huge waste stream, which for us is a huge opportunity. And it's only going to increase. So somebody needs to recover the metals from them so that it can be fed back to the next generation.
How about you?
Big data becomes a real problem with imaging sensors, and especially spaceborne imaging sensors. You have a lot of data and processing and downlink issues. So if you can do robust classification and characterization to pare down your big data into what it is you're really interested in and the absolute information content that you're after, usually it's not all of that, you can't possibly comprehend it. Use that to pare down to what the relevant information is to provide that down.
Right, yeah. Fantastic. Well, thank you both so much. Those were really fascinating presentations. Can you please give these two a huge round of applause? Finish bang on time. Thank you so much.